In this video, I want to talk about special matrices, which are a little bit like upper triangular matrices, and they're called matrices in row echelon form. The reason that these matrices are important is that they correspond to systems, linear systems of equations that are easy to solve. So our strategy for solving a linear system of equations is, now some of these are easy to solve just by looking at them. So if it's easy to solve, just by looking, then go ahead. If not, find a nicer linear system of equations that has exactly the same solutions and solve that. Now this raises a couple questions. First of all, what types of systems are easy to solve? Second of all, if we're given a linear system of equations that doesn't have a particularly nice form, what do we do to it to get a system that's nice? And question 3, given a nice one, exactly what do we do to solve it? Well, today I'm going to talk about answers to question 1 and question 2, and we'll leave question 3 for another time. All right, first of all, question 1. What types of LSEs, linear systems of equations, are easy to solve? Now, if the matrix has the form row 1 has a 1, and then star just means anything else. 1, star, 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 something, something, something. And then the second row has a 0 and a 1, and then something, something, something. And if every row has a first non-zero entry which is equal to 1, and that 1 appears further to the right than the previous one in the previous row, then that's the form that we're looking for. That's the row echelon form. So if a matrix has that form, then the corresponding linear system of equations is easy to solve. And that form is called row echelon form. Alright, second equation. If we're given a linear system of equations, or a coefficient matrix, where the zeros and ones and other entries are not arranged in quite this nice way, what do we do to it to get to a system that has this form and has exactly the same solutions as our original system of equations? Well, there's three things that we can do to a system of equations that don't change the solutions. One is we can change the order of the equations. In particular, we can swap two equations. Second thing we can do is we can multiply any equation by a constant. If we multiply both sides of an equation by a constant, then the equation has the same solutions as before. We'll just write k for a constant. Could be any constant. If we multiply both sides by 0, I guess we still get an equation that's true, but what we get is 0 equals 0, which doesn't give us much information. So we're going to be multiplying both sides of an equation by k not equal to 0. And the third thing we can do is we can replace an equation by itself plus a multiple of another equation. I'll write k times other equation. It turns out that by using a combination of these steps, maybe multiple times, we're certainly going to end up with a matrix that has row echelon form. So let's do an example. In fact, I'm going to do example 248 from the book. Because I think this example is going to be better if somebody says it out loud instead of just reading it in the book. So let's say we start with this matrix 2, 1, negative 1, 3. 1, negative 1, 2, 1. Negative 4, 6, negative 7, 1, 2, 0, 1, 3. Now I've erased the row echelon form matrix, but what we want is a matrix that has where the first row starts with 1, and then we have anything, anything, anything. The second row starts with 0, and then has a 1 sometime later, followed by anything, anything, anything. And the third row starts with a 1 later than the ones that are in the first two rows, and then after that anything, etc. So our first goal is to put a 1 in the upper right hand corner. And we can see a 1 right here, and we're allowed to swap two equations. So let's just swap those, and then we'll have our first 1 in the right place. So I'm going to circle 1 to mean equation 1. I'm going to circle 2 to mean equation 2. So we're going to swap equations 1 and 2 here. And then we get 1, negative 1, 2, 1, 2, 1, negative 1, 3. And the other two equations stay the same. Negative 4, 6, negative 7, 1, 2, 0, 1, 3. Alright, now we're starting with a 1 here. We want to have all zeros below it because we want the initial 1 of row 2, row 3, and row 4 all to appear further to the right of this 1, and they'll have nothing but zeros in front of them. So let's use this 1, and we'll subtract multiples of equation 1 from the other rows to get rid of the 2, get rid of the negative 4, get rid of the 2. So to get rid of the 2 first, let's subtract 2 times row 1 from row 2. So row 2 becomes row 2 minus 2 times row 1. And if we do that, so rows 1, 3, and 4 will stay the same. 1, negative 1, 2, 1. 2 minus 2 ones is 2 minus 2, which is 0. 1 minus 2 negative ones is 1 plus 2, so that's 3. Negative 1 minus 2 twos is minus 1 minus 4, so we get minus 5. 3 minus 2 ones is 3 minus 2, which is 1. And we'll copy the other rows. Negative 4, 6, negative 7, 1, 2, 0, 1, 3. Now to get rid of this negative 4, because we want the first non-zero entry of this row to be further to the right, we can add 4 times the first row to the third row. So let's say row 3 becomes row 3 plus 4 times row 1. So if we do that, negative 4 plus 4, 1, well, I'll copy the first two rows because those aren't going to change. 1, negative 1, 2, 1, 0, 3, negative 5, 1, and now we do something. Row 3 becomes row 3 plus 4 times row 1. Negative 4 plus 4 is 0. 6 plus 4 times negative 1 is 6 minus 4, which is 2. Negative 7 plus 4 times 2 is negative 7 plus 8, which is 1. And then 1 plus 4 times 1 is 5. Alright, now I've got zeros down here. I want to get a 0 in the fourth row also. Now we do have a 0 in the second position of the fourth row, which is kind of nice, but I'm afraid we're going to ruin that in our next step. But that's okay because we'll be able to put a 0 again there later. So let's see. If I want to use the first row to get rid of this 2, I'll subtract 2 times the first row from the fourth row. So row 4 becomes row 4 minus 2 times row 1. I'll copy row 1, 1, negative 1, 2, 1. Copy row 2, 0, 3, negative 5, 1. Copy row 3, 0, 2, 1, 5. And now the fourth row becomes fourth row minus 2 times the first row. 2 minus 2 ones is 0. 0 minus 2 negative ones is positive 2. 1 minus 2 twos is 1 minus 4, which is negative 3. 3 minus 2 ones is 3 minus 2, which is 1. Alright, now we want the second row to begin with a 1 after the zeros. So one way to do that would be to divide the whole row by 3, because we're allowed to multiply both sides of an equation by k. We can think of the first 3 numbers here as the coefficients on the left-hand side of the equation, and the last number as the coefficient on the right-hand side of the equation. If we do that, we get fractions. And when we're doing these row operations, I think it's best to avoid fractions whenever possible. So instead of dividing by 3, I'm going to subtract the third row from the second, because 3 minus 2 is 1. So row 2 becomes row 2 minus row 3 is what I'm going to do. So we have 1, negative 1, 2, 1. 0 minus 0 is 0. 3 minus 2 is 1. Negative 5 minus 1 is negative 6. 1 minus 5 is negative 4. And then we'll copy 3 down exactly as it was. 0, 2, 1, 5. And 4 down exactly as it was. 0, 2, negative 3, 1. Alright, now I want the third and fourth rows to start with 1s, but someplace to the right of this one. So I want to get zeros everywhere in the column below this one. So I could subtract 2 copies of row 2 from row 3. And I could also subtract 2 copies of row 1 from row 4. So let's say row 3 becomes row 3 minus 2 times row 2, and row 4 becomes row 4 minus 2 times row 2. Now it's probably best to do one row operation at a time. I'm going to do 2 here, which is kind of living dangerously, I think. But hopefully I'll do it correctly and won't mess this up. So row 1 is staying the same. 1, negative 1, 2, 1. 2 is staying the same. 0, 1, negative 6, 4. 3 is going to be 3 minus 2 times 2. 0 minus 2 zeros is 0. 2 minus 2 ones is 0. 1 minus 2 negative 6s is 1 plus 12, so that's 13. 5 minus 2 negative 4s is 5 plus 8, so that's 13. And then do the same thing with row 4. 0 minus 2 zeros is 0. 2 minus 2 ones is 0. Negative 3 minus 2 negative 6s. Oh boy, lots of negatives. Negative 3 plus 12 is 9. And then 1 minus 2 negative 4s. 1 plus 8 is also 9. Alright. Now I want to have a 1 in row 3 further to the right than the ones that I have so far, which begin row 1 and row 2. Now I guess I could subtract a multiple of row 4 from row 3, or I could divide by 13. Normally I wouldn't divide by 13 because I wouldn't want to have 13s all over the place. But in this case, if I divide by 13, I'm just going to get 1, 1. So that's not bad, since everything in this row is divisible by 13. So I'm going to say row 3 becomes row 3 divided by 13. Maybe I'll write 1/13 of row 3. So if I do that, let's see, copy down the first row exactly as it is, 1, -1, 2, 1. Copy the second row exactly as it is, 0, 1, -6, 4. Third row becomes 1/13 of the third row, so 0, 0, 1, 1. And then we have 0, 0, 9, 9 in the fourth row. Alright, so I want the first non-zero entry, the fourth row, to occur further to the right than this one. So I'm going to subtract 9 copies of the third row to get rid of the 9 here, to make a 0. So row 4 becomes row 4 minus 9 copies of row 3. Now while I do that, I'm going to get zeros in both of these positions, but that's okay. So 1, -1, 2, 1, because the first row doesn't change, second row doesn't change, 0, 1, -6, 4. Third row doesn't change. And then the fourth row becomes 0, 0, 9 minus 9 ones, 9 minus 9 ones are both 0 and 0. So this matrix has the row echelon form, and that's going to correspond to a system of equations that is very easy to solve. Now while we were doing these operations that are called row operations, to get from our original matrix to this nice matrix that has row echelon form, I wrote down my own shorthand about what I'm doing. Row 2 becomes row 2 minus 2 times row 1. Now everybody has a different shorthand to remind themselves what row operation they're doing at each step. And I think it's not essential that you use exactly the same one that I used. It's not essential that you use exactly the same one that's in the book. You think of something that works for you, but the important thing is that every time you do a row operation, you have to write down what you're doing. Because after all these computations, there's a good chance that you're going to make a mistake somewhere. And you're going to have to go back and figure out where you made a mistake. And if you don't have notes to tell you what you were trying to do at each step, it's going to be very hard to find the mistake. And I guarantee that you're going to make mistakes sometimes, because even professors doing this make mistakes. So we'll try this. This would probably be a good thing for us to do during the Zoom session, to do more examples of row operations. We'll be doing a lot of this semester. The end.